charge transport in semiconducting materials determines the properties of all electronic and optoelectronic devices that we use. So to improve these devices, it is absolutely necessary to perform simulations of these materials. For simulations of these materials, we need high-performance computing resources to make these to perform these simulations as fast as possible. So depending on the type of the material and on the charge transport mechanism in the material, different types of simulations are performed. So first class of materials that we investigate are disordered organic materials. So in these materials, electronic states are localized and charge transport takes place by hopping from one side to another. For these materials, we use methods that are capable of performing electronic structure calculations for systems containing or the order of 10,000 of atoms. And for that, we use some very specialized methods. After we perform this, then we still need to do one more step, and then we have a multi-scale method that bridges the scale of the order of few nanometers to the scale of the order of 100 nanometers, where we can eventually get, for example, the temperature dependence of the mobility in the material. For second class of materials, which are conventional crystalline materials, such as, for example, silicon that is widely used, we first perform the calculations based on density functional theory. Using these calculations, we get information about electronic states in these materials, about the vibrations these materials, so-called phonons, and on the coupling between electrons and phonons, which actually limits the charge transport in the material. To perform these calculations of electronic phonon coupling, we also need some very specialized methods, because these electron phonon coupling parameters are needed on dense grids of electron momentum and phonon momentum, so that the final results of the simulations are reliable. And there is a third class of materials, which is somewhere in between the first and the second class. In these materials, it is suspected that the electron phonon coupling is relatively strong, so that the formation of particles, so-called polarons, which can be thought of as mixed electron and phonon states, takes place. And for these materials, we are currently developing methods that will be able to simulate the mobility of charges, which are these polarons, and we are doing this in the framework of a project which is funded by Science Fund of the Republic of Serbia. The name of the project is Palmorem.